So please welcome Andrew Sorensen, all the way from Queensland. There you go.
Thank you. Cheers. Well, it's very nice to be here, and I mean, what a wonderful venue for a musical concert. So I feel very privileged to have this space to play in today. So the title of my talk, Programming in Time, and really the essence of what I'm going to be talking about, in a sense, is this idea of programming the world. So when I talk about programming the world, in a large sense what I'm talking about is programming real-time systems, and in particular the idea of programming real-time systems in real time. So this idea that we can live code real-time systems. But if you think about live coding of real-time systems, there's sort of two contexts that you could imagine that happening in. One is the idea where you're live coding the underlying real-time system. So you're sort of using some higher level language to sort of control a real-time system that's running underneath. But there's a second idea that I'm more interested in, which is the idea of actually live coding the real-time system itself. So we're actually looking at live coding the real-time system in real time, real time. So the real-time systems that I'm particularly interested in are these systems that are connected to the environment in some way, to the acoustic space in the context of audio, which we're going to be talking about quite a lot today. So this being the acoustic space that we're all sharing. And it sort of highlights this idea of firm real-time systems. So if we kind of imagine that on the one side we have hard real-time systems, and actually Martin gave a great example of a hard real-time system today, a sort of a short-range defense gun for a ship. And you can imagine this hard real-time system, and it's sort of looking at this missile that's coming in, and it's sitting there and it's going, garbage collect, shoot down the missile. Garbage collect, shoot down the missile. You know, it's not really a choice, is it? You've got to shoot down the missile. So that, if we take that as being a hard real-time system on the one side, then on the other side we kind of have the idea of a soft real-time system. And a soft real-time system, in some sense, is, you know, it's a little bit wishy-washy in the sense that it's sort of like we want to try and hit all of our deadlines, but if we miss a couple, we'll hopefully make up for them a little bit later, and we've got a little bit of flexibility. But sound and music aren't really like that either, right? On the one hand, no one's going to die if I miss a couple of timing events in this musical performance. But at the same time, it's going to really affect the quality of the performance. It's going to sound bad if we start missing events. So we really don't want to miss any events. The other thing is that our human oral perception is actually very sensitive. So we hear rhythm down to sort of about 30 milliseconds or so, but then in fact we hear timbral changes right down to the sort of millisecond range, 1 millisecond. So compared to our other sense perceptions, which are actually significantly higher than that, our auditory system is actually quite sensitive to timing errors. So as I mentioned, the sort of real-time system that I'm going to be focusing on today is audio-digital signal processing, and above that, sort of the idea of music at sort of more of the note level. And we'll see examples of working at this note level today, and we'll also then see deep diving down below the note and starting to change the real-time audio signal processing system on the fly as well. And we'll get into that a little bit later. So, as well as talking about programming the world, though, the other idea that is maybe perhaps even more important that I'd like you to take home from this talk is the idea of programming in the world. And this is sort of the idea that programming can be about a journey. It doesn't have to be always about a product. So very often we get carried away with the idea that programming is always about delivering something, some kind of artifact, some product at the end of the process. But one of the things that I'm exploring a lot is this idea that the journey itself is the process. So what you'll see in the performance that we're going to do later is that the performance will actually start from a blank screen, and I'll start programming up the performance, and you'll see this sort of performance evolve over time. The interesting question is, the code at the end of the performance, or at least what's left in my text buffer, really won't be a representation of what you've just heard. It's only the whole history of all the changes and the modifications to the code through time, this sort of computational journey that is what it was all about. So then we have this idea that the thing at the end really isn't very representative of what we've been listening to. So then another thing that's worth thinking about is if we're changing these things on the fly and I'm producing something that affects the environment, so in this case, this sort of audio that's going out and it's bouncing around the room, and I'm listening to that signal and I'm making changes to the program to make the music adapt to what we're listening to, I'm sort of embodied in the space. My sense perceptions, my ears, are part of the computational solution. I'm helping the computer to generate the music, but I'm listening to the music, and then I'm changing the code to help the computer generate the music. And so there's this sort of cyber-physical coupling. There's this idea of me and the machine and the process and the environment, this space that we're in, and the fact that this is one sort of integrated, coupled system. So just a little bit of background. I've actually been doing this kind of very crazy arts performance practice for about the last 10 years or so, which is this idea of live coding these musical performances in real time in front of an audience. And so here you can see a picture, you can see my code, well, you can see my the bottom of my log really on the screen behind me there, and I'm sitting in here. This is a relatively small performance, but of course there are also very large performances as well. So this is an example of a large performance, and also what we have here is a duet. So there's actually two of us programming here, and you can see we've got both screens. You can see a screen on the right there and a screen on the left. There's a little bit of backstory to this performance, which was that it was horrible. This was a horrible, awful, disgusting, revolting performance. Everything went wrong, except the picture. It's just a beautiful picture. There's lovely lights coming down. You can see the smoke in the room, you know. So every time I bring it up, I kind of have to relive the horror. But I like the horror picture, you know. It's a tricky problem. It's worth pointing out, though, that these performances don't always happen in the context of electronic music. So here's actually a picture of me playing at the Brisbane Conservatorium, and I'm playing on two robotic disclaviers. So my computer's actually connected up to these two pianos, and this performance then is completely acoustic. There are no speakers involved in this performance. The computer's still generating all of the music that people are listening to, but the music itself, the acoustic space, is all being rendered by the pianos, the robots that are playing the pianos. And in fact, in the context of this performance, this was a sort of a jazz style. So it was really quite removed from electronica, for example. It was really quite a jazzy, acoustic musical performance. But it's, certainly true that most of the activity in this space happens in the electronic music scene, in lots of different variants of the electronic music scene, so experimental music scene. This is actually from a sort of an algo rave performance. Algo rave, short for algorithmic rave. An algorithmic dance party where everyone's grooving along to their, favourite computer-generated algorithms. Sounds incredibly geeky, I know. I mean, what are you thinking? But it's quite a lot of fun, actually. So this photo was actually taken in the belly of a ship called the MS Stubnitz. This is kind of right down in the hold of the ship. It's actually a really amazing arts venue. It sort of sails around Europe, stopping at various ports along the way, putting on nightclub performances, but also things like dance performances and theatre performances and other kind of types of activity. So what I'd like to do now, though, is I'm going to get into doing a musical performance for you in a minute. But the first thing I want to have a little bit of a talk about is when we talk about live coding, most people, the word live in the sense of live coding is in relation to being on stage, for example. So usually our community talks about live coding as some kind of programming that happens as part of a presentation is sort of the usual format. But for me, the liveness is different, and it's much more connected to this idea of the physical environment and real-time systems. So I just want to sort of unpack that a little bit before we get started. So if I start in my REPL here, I've already made a start, but in my REPL here, it's worth starting by asking the question, when we're live coding, really what is it that we're doing that's any different to the sort of venerable REPL that's been, in existence since at least the 1970s? So we've had this thing for 40 years, so is there anything new that we're contributing at this point? So, we certainly have this idea of a dialogue, right? This communication that's happening between me and the machine. I can ask a question of the machine and it responds with this, 6. I can say, I can define, for example, a variable, let's say something like that, and we can say, we could say something like, this. And then I could ask the question of the REPL, what is the result of amplifying chocolate with coffee, right? A very important question. Could only be one possible answer to that question. So this interactivity is something that we're used to using. It's something that's been there for a long time. And in fact, if you think about it, it's actually also very similar to the Unix shell, right? Which then gives us this ability to also talk with a real-time system. So, I could do something like, say, list the current files in my directory, or, what's my current working directory, for example. And so all of a sudden, the REPL starts to behave a bit more like a Unix shell. So again, this idea that these things aren't new, these are things that we've been working with for a long time. So let me now start to get into what I think is new, this kind of new idea of liveness that I'm sort of talking about. And I'm going to start with a fold function. So what I'm going to do is I'm going to just fold over the first 100 integers. Okay, so we fold over the first 100 integers, we get the result 5050. Okay, so of course, we could go the other way. We could subtract. We get minus 5050. Okay, nothing particularly exciting going on there. Okay, now let me bring up a definition of the fold function. And what I'm going to do is, I just want to print out the accum. So we're going to sort of inspect this accum value every time around this recursive call. And so if I, we'll do the same thing up here, range over 101. And so you can see down in my log, it's sort of printed out all of the accums. We're sort of, reducing this down to 5050. But this time what I want to do is I just want to slow it down a little bit. So we're going to run this with a little sleep in here. So this stops every time around. We're going to run it again. And of course, it's what we'd expect. We're just going to see these things reducing down. So let me just let that finish. We should get to 5050. Now, I'm sure you'd all trust me that if we started the fold function with a minus, we'd get negative 5050. And it's worth pointing out at this stage that this is a pure function. This is a referentially transparent fold function. Now, what I want to do now is I want to show where this liveness comes in. So let me start this again. And this time what I'm going to do is I'm going to redefine this function mid-execution. So we compile in the change, and all of a sudden this accumulated value is going down, okay? Which is actually quite scary if you think about it, because we've completely lost our referential transparency, right? In the negative case, we should be getting minus 5050. In the positive case, we should be getting positive 5050. But what's perhaps even more scary about this, let me just put this back again and start this up again. Okay, we're accumulating up, and let me do it now. Right. And we don't even get the same value twice, right? So now all of a sudden, exactly when I make the change has a fundamental impact on the result that we get. So all of a sudden, the timing of when these things happen matters a great deal. Now, there is a different way we could think about this. So rather than maintaining this observable state, we could actually look at this in a different way. We could say what we're going to do is when we make a change to the text, when we maintain our state, we get this divergence between what we're seeing in the text and what we're actually getting in the executing program. But we could think about it a different way. We could say, instead of allowing that divergence, we're actually going to say, no, we're going to stop everything, we're going to throw away that state, and then we're retroactively going to restart that function. But there are a number of problems with that. It maintains our referential transparency, but all of a sudden we've got problems like, for example, if we've been running a long-running physics simulation, which might have been running over hours or days or weeks, it's completely unrealistic that we could just throw away all of that state and start again. Another problem is that if it's a system that's actually working in the physical environment, so let's say a robot system, it's controlling eWally, for example, and the robot's out there and it's moving around in the world, and then we get it to pluck a flower off a tree, Well, we can't then all of a sudden say we want to rewind state and go back in time because the flower's not going back, okay? So there are changes that affect state in the world, like, for example, sound in this room. Once that sound is out there, it's actually going to reverberate around the room for a certain amount of time. We can't pull it back, okay? So there are some physical restrictions on some of the things we can do. But one of the other problems is that often it's actually the observed state that led us to the change in the first place. And that's actually really kind of the key point I want to make. So let me just make that a little clearer. So what I'm going to do is we're going to play a note here. So I'm going to replace the print line, and every time round, let me also do this before I forget. Every time round here, what we're going to do is we're going to use the accume, its frequency. We're going to effectively treat accume as a frequency. I'll make this volume a bit softer. Made it too soft. I'll come back. We'll do it again. Just because I know you want to hear it, right? Okay, here we go. I'll make that a bit louder. Thank you, good night, thanks for coming. That's me done. So now we've, thank you, yes. So we've just run it through, but now what happens if we start changing the behaviour now, right? So I'm talking about this idea of sort of steering this algorithm through time. So let's have a go at that now and see if we can make a little melody, right? So what we're going to do is we're going to start this again. Wasn't that beautiful? Yes. The point being that you can see that it's the state, it's actually me listening to the pictures now. We're not seeing any logged printout, it's me listening to the pictures and not very well trying to change pluses and minuses to sort of make it go along in a wiggly pattern. Musically awful, but I hope you get the idea of the point. So now let's now actually try and actually use these ideas to do something a little more musical. So I'm going to get rid of this and we'll start again. Let's just blow this away. And we're going to start with a little design pattern which we kind of call a temporal recursion. So the idea of this is I'm going to try and talk through a little bit about what I'm doing so you get a bit of an idea about what's happening behind the scenes. So this temporal recursion, I'm going to call it left because I'm going to use it to mimic the left hand of a piano. So we give our function a name, and then what we're going to do is I'm going to give it a duration. I'll come back to that in a second. Let me just fill in some blanks here. Okay, now I'm about to start this off, but what's going to happen is that we're going to call the function's going to play a note, and then the function's going to schedule itself into the future to be invoked again. So this idea that this function then becomes a recursion through time. It schedules itself on the scheduler, calls itself back in the future, schedules itself on the future, and of course it's passing potentially changed arguments each time around, etc. So I'll start this up. I should also say the numbers that we're dealing with today are usually around pitches and volumes. And we're working from 0 to 127 for pitches and 0 to 127 for volumes. So 0 being very soft, 127 being very, very loud, and 0 being the far left-hand side, or 1 I should say, being the far left-hand side of the piano, and 127 being the far right-hand side. It's actually a bit wider than a piano, but for all intents and purposes that will be fine. So let me start this up now. Okay, so we can hear that each time around it's calling this 60. So 60 is a middle C, so we're getting this middle C sound on the piano. And what we could do is we could add a second offset in here. I'm going to say I want to do the same thing, but this time I'm going to offset this second note by a little bit. And I'm also going to push it down, so it's now going to be the fifth of what we're listening to. So now we've got this little offset of this second note happening. Now I'm going to introduce some evil global state here for reasons that will hopefully become clear a little later. And let me just do this. Now what I'd like to do is I'd like to have this harmonic progression kind of somewhat probabilistically moving around. So I'm going to use a little trick which is to use a Markov chain so that we can kind of use previous events to determine future events. It's going to be a very simple Markov chain, but it will help us to have some kind of non-determinate behaviour in the program. So we're going to just set the root here. And so the Markov chain itself here really is just this, the first line with the 60 to 58 is basically saying that every time we get a 60, we're going to choose, we've got a 100% chance of getting a 58, and then the line below it says every time we get a 58, we've got a 100% chance of getting a 60. So not particularly exciting at the moment, but we'll just click this in. Of course, each time around here, we're making these changes and just sort of hot swapping them in on the fly. So we can get a bit more adventurous and we can, add a few more pictures in here. So we'll go down to 56 and maybe 56 will go down to 55. So now up here 58 has 50% chance of going to 60 and 50% chance of going to 56. We could go back up to 58 and then down here we could go to 55, we could go to 50, 56, and here we could go to 55. And so now we've got these kind of probabilities that are going to sort of randomly move us around. And these numbers are basically just following some very simple musical harmonic principles. So when I evaluate this in, then it'll start sort of expanding out what its sort of harmonic vocabulary is. Now, this is all a little bit boring, so what we'd like to do is, no pianist has, well, I guess some pianists have only one left hand, but we're going to have a two-handed pianist. So I'm going to introduce a right hand here, and this is going to be a second kind of concurrent part that we have running. So we'll just call this right. And what we're going to do here is we're going to use this root value now. So we're going to use root and we're going to say what we'd like to do is the cos R is a cosine. So we want an oscillator. And we're going to cheat. We want to make a pattern, but what we're going to do is we're just going to sample the cosine on the sort of rhythm boundaries, and we'll use the sample point as the pitch that we use for the pattern. And the sinusoid will hopefully give us an interesting pattern. So let's push this in. We're going to use the same thing for volume too. So we're using the same sort of cosine for the volume as well. I'm going to make the piano a little longer here. And now we'll start this up. So now we've got this right hand, and the right hand is going to be circling around this root, right? So the root then forms the center of wherever the cosine is. Now you might be wondering, that sounds kind of okay, surprisingly enough. It's just randomly choosing in this sine wave. How come that kind of matches up with the harmonic structure we've had? Well, because I chose very wisely. So in fact, what I'm going to do now is I'm going to completely break it, and it's going to sound awful. So we're going to change this. We'll put effectively an amplitude modulation on the original cosine, and things will go bad really quick. So this, ready? Cover your ears. Right, so that's what you're usually going to get if you haven't actually very selectively chosen exactly what you're doing with your cosine. So I'm going to turn that down because it's just so bad. Let me just turn that down for a sec. So the way we get around that is we're actually just going to use a very simple set. So we're going to use a set from set theory, and we're going to quantize the scale against the set, okay? So I'm just going to do this based on a musical scale, Aeolian scale, which is effectively just a minor scale. I'll do this, and then what I'm going to do down here is, just change that while I'm here. And then what I'm going to do is I'm going to turn this up and then I'll fix it. So what we're going to do is we're actually going to use a variant of this cosine, which is a quantized cosine, which just means it's going to make sure it quantizes the points. So I'll put my scale in here as the first argument. I'll turn it up and make it sound horrible again. And now when I evaluate it in, it'll start quantizing. So now we can see that it's sort of quantizing all of those points, which is just neatening everything up for us. So we have a bit of piano going now, but what I'd like to do now is bring in a synthesizer. So some synthesized sounds, we're going to use these as a bass. So this will sort of ground the root that we've got happening in the piano. So let's just call this sub bass. and we're going to use a different instrument. This is going to be a synthesizer that we're going to use. Again, we're just going to use this root that we've been playing with, and we're going to use this pulsation. And I'm going to bring this in slowly, and we'll sort of bring up the volume on this. Okay, so we just sort of slowly bring in this synth here. Now, it's worth pointing out, if I just take out the cosine is that we're just playing one pitch here. This is just this root. It's changing depending on what the left hand is doing, but it's just static. The interest in that part is actually just coming from the variation that we have in the volume. So if I actually take that out and just make it static as well. So now you have the flat variant. So that's just playing the same volume every time. And this is putting it back in. Oh, I'm a very bad man. It'll come back in a second, bear with me. Wrong arguments, I'm afraid. La-di-da-di-da. That's what happens when you create millions of notes all at the same time. Come on, work your way through. Okay, so now what we're going to do is we're actually going to bring in a drum kit. So I'll bring in a drum kit, and that's now going to overlay the top of that as well. Okay. Let me just put this back in now. Okay, so let's go with the drum kit. It's nice to be reminded that it's live sometimes, right? I mean, you need to have these things go wrong. So again, we're going to use the same idea. So now we're going to use a cosine to create a drum kit part. So all of the rhythm, effectively, the choice of which timbres we're playing on the drum is again going to come from these cosines. So let's go here and something like that as well. And I'm also going to randomly swoosh these sort of backwards and forwards between the left pan and the right pan. So it's going to be moving between the two speakers. So you should hear that sort of panning between the two speakers now. And we'll expand this out. I'm now just going to put in a couple of other parts, drum parts that is. So. Now what I'd like to do is I'm going to introduce another synthesizer to play up high. At the moment we've just got the synthesizer playing down in the sub-bass, but we're going to mimic what's happening in the right hand of the piano and actually have a synthesizer which is playing a sort of a polyrhythmic and poly-pitched behaviour. So it'll actually sound quite similar to the piano, but it'll have its own sort of individual behaviour. So we're going to use another synthesizer for that, and we're going to go 5/4 there. We'll make this a little bit softer. And we'll make this 0.1. So we've been listening to that harmonic progression for a little while now, so what I want to do is I actually want Sorry. We've been listening to that harmonic progression for a little while now, so I'm going to change it just so you can also hear how much just a little change can actually make to everything else that's going on. So that's the new harmonic texture that we just added down the bottom there. So you can see that you can actually build up some, relatively complex musical behaviours very, very simply. So up until this point, everything I've been doing is at this kind of very high level, sort of note level. But what I want to do now is I'm going to start drilling into the audio signal processing that's going on. So we're going to start changing these instruments on the fly at a signal level. So let's start by, we've got this FM synth doing this sort of higher level. So I'm going to jump over to where that's defined. Oops, wrong one. Let's do it here. Let me just make that a bit smaller. So this is a higher order function. This is a closure that returns a closure. So every note that gets produced, a new closure gets returned, and that closure actually does all the audio signal processing for this particular note, which is where we get our polyphony from. So we could start, for example, by, let's actually just add some white noise to this. So I'm going to add here, I'm going to multiply the amplify by just random. So this is white noise, and we'll start to hear this come into the synth. So I'll just connect this up. Actually, let's connect it up. Can you hear the white noise now that's coming along in the part? So for every note now, there's white noise that's actually following the amplitude curve. We could do something a little more obvious, like we could add another oscillator in here. And I could modulate the frequency of these notes with the other oscillator. So let's pop that in. So you hear that warbling that's happening in the synthesizer now because we're doing this sort of FM synth on it. I'll take that out. We could do something a little more musical with it. We might choose to, let me compile that out again. And I'll take the white noise out too. Instead, what we're going to do is we're going to use that oscillator to almost sort of add a second part, but this time the part will be happening at the audio signal processing layer. We're going to have this oscillator running a couple of pitches higher than the rest of the synth. And note that all we're doing here is we're like literally just doing the math, okay? So to add these signals together, we're just summing the samples as they go through the system. So let's use the amplitude that's coming in and the frequency that's coming in, but we're going to multiply the frequency by 2 to kick it up by 1 octave. Compile this in. So now we have that second sine wave that comes in, and what we might want to do is punch it up another octave. So it just gives sort of this nice tinkle to the top of the synth as it's going around. So what we're interested though is I just want to show that we can dive all the way down. So what I introduced there, this oscillator, this O3, this osc_C, could for example be calling out to a C routine. It could be calling out to a C library that did all of this. But the whole idea with Extempore is that we want to be able to compile all of these things throughout the signal chain, all the way down to the device driver. So I'm just going to jump across to the oscillators source now. And so here we have that oscillator. And in fact, if we multiply the frequency of the oscillator, it's going to take every oscillator in the system and double the octave of all of them at the same time, which may not be exactly the behavior you're after, particularly when you're writing your security routines, but that's not our concern here. So let's connect that up. Okay, so we're getting quite a long way through the stack now. We really only have one level left, which is actually the DSP's callback routine. So on my little audio device here, that's running at 192K. So that's 192,000 samples per second times how many channels we're running. So in this case, 2 channels. And we have to fill buffer sizes of 32 samples. So that effectively equates to about 6,000 interrupts per second, which means that we've got about 160 microseconds or so to do all of the audio signal processing that we need to do to fill that buffer before the sound card requires it to be there. The thing that makes this tricky is if we miss even one of those deadlines, then you're going to start getting glitching in the signal that you're listening to. So if we jump across to this now, search for DSP. So this is basically the bottom of the tree. So this is the thing that's being called back from the device driver every single sample for all of those 192,000 samples. And again, we could just do something simple like add white noise down the bottom here. So let me just connect, actually I don't have to, I'll compile this in. And so you can hear that white noise that's now going through the signal. And again, we've just summed this in. It's really just to demonstrate that we're making these changes all the way down to the bottom level. And it's interesting that you can see this is where the synth and the Fox and the sampler are all defined, so the instruments that we're using. And of course, just by multiplying the output of the synth, for example, we can deduct the gain of that synth by a half. So the synth's now softer, we can multiply it again, bring it up, get rid of the white noise. Okay. And of course, you know, when you have no idea how you're going to finish something, the way you want to finish something is with a slow, steady fade, right? So then we can just start taking all of this out a little bit by a little bit. Okay, so there you go. Thank you. Okay, so that's fun, right? So I enjoy it anyway. So what we're going to have a look at now, though, is that some work I've been doing with some colleagues at the Australian National University, Ben Swift and Henry Gardner, which is working with plasma physicists, and we're trying to sort of introduce some of these ideas into their work practices so that they can look at starting to steer their computational simulations in real time. Now, today I've only got my laptop, but what you have to sort of keep in mind as we're having a look at this simulation today is that the usual context for this is running on a distributed compute node. So we actually fire out the code onto all of these nodes on the fly when we make a change, and it compiles in and hot swaps them on the fly. So let me just start up the PICSIM here. And I'll just make this transparent. Okay, so this is a PIC simulator. This is a particle in cell simulator. And effectively what we have is we have all of these electrons and they're all floating around in space, and that space is being dictated by an electromagnetic field. So the particle in cell simulation is effectively just solving this problem of taking these the velocities of the particles, which are affecting the field, and the field is affecting the velocities of the particles. And of course we can do the kind of usual higher level things that we can imagine. So we can go, let's change dt to make it all run a bit quicker, make it even run faster. So this is just speeding up the speed of the simulation here. Of course, because we're physicists, we don't care about the real world, and we can run time backwards. I shouldn't say things like that. So let me slow this down again now, so we'll put it back the way it was. But again, really what we want to do when we're exploring these ideas is that we want to give these physicists the ability to change this code at a very low level. And sort of the point of this exercise is that this is actually, there are hundreds of thousands of particles, and it's quite a heavy compute problem. So I don't want you to, don't think of this as a graphics example. This is not graphics particles that we're talking about. This is the only reason we have this is so that somebody can actually sort of follow the behavior of the system while it's running. So if we just have a look at a sort of a fictitious example, which is that I'm going to just randomly, well, not randomly, I'm going to grab the first 100 particles and I'm going to take them out of their normal positions and I'm going to physically force their position. So let me just do that for 100 particles here. And again, we're going to just compile this in. So now you can see the cluster of these particles that we're sort of shifting through the middle there. And you can see that it's starting to have some impact on the particles around it as it moves it through, because we've now clustered all these electrons into this very small space, and we're controlling where they are. But as we're watching it, of course, what we'd like to do is, just play around with the effects of this. So as we change and modify the behaviour of this code, we're starting to see what effect this has on the simulation environment. And the thing that we're interested in is, how will computational physicists use this to change and evolve their simulations over time? Of course, we're just adding more and more energy to the system all the time at the moment. We're not doing anything to take it out. So it's eventually going to explode. But it's really, again, this idea that if we can imagine this happening on a cluster with one node at the front, that's actually then the visual node, the visualization node for the physicist who's actually changing their compute across the whole cluster. That's an idea that we hope will be interesting. So let me just stop that and get rid of that and go back to here. So just sort of to tie a few of these things together to finish off, I've been very lucky. I work at this university. This is a brand new building that we have in the university. This is the new Science and Technology Precinct. And one of the things that happened when this building got built was that there was a big interactive display that was built as part of the centre of the lobby area of this building. So this is the cube. Looks very cube-like, right? I mean, that's what happens when you get architects involved. So originally it was supposed to be a cube. So you can see that we've got this wedge here. It's an extremely large space. Along the bottom we have 20 multi-touch panels. They're all interactive, multi-touch interactive panels. And then all the way along the top we have this edge-blended projection surface. So the top part is all effectively static and the bottom part is all interactive. This is it running with a Great Barrier Reef simulation. So effectively targeting high school students. So high school students can come in and they can kind of play with this virtual reef and kind of understand how various species behave and interact, and just to give them an understanding of the ecosystem of the Great Barrier Reef. So my project for this was actually looking at a sort of a physics wall. So the idea is that hopefully we can get early high school kids to come in and they can play with this wall, and while they're having fun playing around with all of the kind of physics that they're interacting with, we hope that they'll actually get interested in some of the mathematics behind it. So in the video I'm about to show you, you'll see a bunch of black panels come up that actually the black panels basically just have all the math, for want of a better word, so hopefully they'll get a bit inspired. One of the things to keep in mind when you watch this video is that this is running on a cluster, so all of these screens are actually running in high def. So to be able to render this at high def, we actually have to run this on 8 different machines. So to keep all of this synchronized, as you'll see when blocks flick across all of the screens, we're talking about synchronizing all of this across 8 different nodes. So just bear with me, I'll just run a quick video for you. Okay, I think you get the idea of that. So yeah, just to finish off this same idea, that one of the cool things about working on this project with Extempore, which I'll get into in just a sec, was again that I can kind of sit here with the wall running all of the time, and I can connect through my laptop, make changes, and it's blasting that code out to all of the nodes on the fly, compiling it on the fly and switching it in, potentially while people are using the display. In fact, always while people are using the display. And this kind of gives us some nice serendipitous opportunities, because often somebody will come into the space and they'll be playing around and they'll have trouble making something work, and you can actually sit and change and modify the behavior of this while they're interacting with the system, which is kind of nice. So we're nearly at the end. So let me just finish off very quickly with a quick overview of Extempore, which is the programming language and environment that we've been looking at for all of these examples today. So this is something I've been working on for the last sort of 3 or 4 years now. It has a couple of features that make it somewhat interesting. One is this idea of being strongly timed, by which really what we're talking about is that there's a real-time scheduling engine built into the language and environment that gives us some temporal semantics. So particularly things like we try to have some kind of guarantees over the execution start time of code, and also on execution deadlines, for example, how long a piece of code will run. We actually have exception handling to manage that. It's both distributed and heterogeneous. Heterogeneous in particular, not just obviously multiple CPU architectures, x86 and ARM, but also, for example, targeting GPUs as well as CPUs. It's concurrent, supports sort of cooperative and preemptive concurrency. This idea of being wide, which we've talked about in terms of audio, being full stack, the ability to make changes to code all the way down through the stack. It's high performance, but perhaps more importantly, it's designed to be deterministic, so that we have reasonably good idea about how our code's execution profile is going to be at runtime. I'm sure you couldn't help but notice that it looks like a Lisp. You know, it has S expressions, lexical closures, tail recursion, Lisp macros, and it looks very much like Scheme. It has a Scheme-like block structure, except really it's not a Lisp. It's statically typed and supports type inferencing. It has expressive data representations, by which we really mean sort of architecture with primitives and things like SSE register support, for example, as a primitive. Supports reified generics and specialized code generation. Fast, as I said, but again, more importantly, this idea of being deterministic. And we're at the end. So thank you very much.